Okay, so how is everyone today? Good? All right. So, last time we were in the midst of trying to say what the fundamental theorem of analysis is. It's sort of like the fundamental theorem of like little analysis. So, for any of y'all that are math majors, or if you're an engineering, physics, science major, but you're planning on, what am I trying to say? Leaning towards the mathy side of it. Like, for example, there's a lot of math in physics if you choose to go that direction, and there can be a lot of math in chemistry if you choose to go that direction. If you do that, at some point, calculus kind of stops, kind of cuts into two bits there, and one of them, one of the directions you can go in calculus is called analysis. So, like right at the beginning of that cut, you get this thing called what is more or less the fundamental theorem of analysis, but right at the beginning. So we had said the following last time. We had said that in the first place, we had defined the set of all lower bounds of a set X. Okay, so this is the set of all lower bounds of set X, which is a subset of the reals. Okay, and an example of that would be the set of all lower bounds of the set, say 14 to 24, like that. Okay, it's sort of obvious just looking at it, but to make it visually as obvious as possible, what we're saying is that here's that set right there. So here's the set 14 to 24. And then underneath it, I'll draw another number line. And then a lower bound is a point that doesn't necessarily have to be a red point. It could be any point. So a lower bound is any number that's less or equal to all of the red numbers. So, like for example, 3 is a lower bound, and but 23 is not a lower bound. It's less than some of the red numbers, but not all of them. And negative a million is a lower bound. So what is the set of all lower bounds for that set? Right. So then 14 is a lower bound, because that green point is less or equal to all those red points, and in fact anything to the left of it is. So the set of all lower bounds of this particular set is negative infinity to 14, including 14. So to make another one, I could say, for example, I could say suppose we have this sequence, AN is 1 over n. So we've got that sequence. That sequence is so important it has a name. What's its name? A harmonic sequence. And now I could say this. I could say let set X be the set of all AN, just such that n is a positive natural, which is to say that set X is 1, a half, a third, a fourth, ... So it contains all of the numbers which are part of the harmonic sequence. So fine. Then I could ask, does this set have a minimum? Does set X have a minimum?
0.
So how about the minimum? of set X, does it have a minimum? It doesn't, right? In some sense, you kind of want to say 0, but you can't say 0. Why can't you say 0? It's not in there, right? So the minimum of a set has to be in the set. So if you were to plot set X, then, you know, there'd be this open point there. You know, you can't have that point. That's not it's not there. But then, you know, you'd have 1, you'd have a half, you'd have a third, you'd have a fourth. You know, and the points would get really, really clustered the closer you get to 0, right? No matter how close you look. But is 0 in there? It's not in there. So what's the minimum of set X? It doesn't exist. But you know, if I ask about the set of all lower bounds of set X, then you know, what points are lower bounds? For example, how about 0.9? Is that a lower bound? No, because there's red points that are less. So how about 0? Is 0 a lower bound? Yes. Is 0 less or equal to all red points? It is. So 0 is a lower bound. What if I just get a little bit bigger, like say 0.01? Is that a lower bound? No, because there's going to be a harmonic number less than that. Okay, so the set of all lower bounds of the set of all harmonic numbers is this, negative infinity to 0. So even though, you know, and I could say the same thing about this set, a similar thing about this set, the set open 14 to close 24, does it have a minimum? It doesn't have a minimum. But in some sense, you want to point at 14. You want to point at 14. Now, the minimum of this set is not 14. Why is it not 14? Because it's not in there, right? The smallest red point isn't 14 because it's not a red point. And you can't point at any other red point and say that's the smallest, because there's always going to be a smaller one. Okay, but you know, nevertheless, we're talking about the set of all lower bounds. So what we really need is, instead of minimum, we need a new name, and the new name is this. So 2. The infimum of set X. So infimum of set X is infimum of set X, and then what's its formula? No, this is just any old X. How do we calculate it? So minimum is you find the smallest red point, if there is one, but there might not be one. How do we do this? So this is the last thing we said last time.
Max of LX.
Yeah, it's the maximum of the set of all lower bounds. Okay, so what I want you to see is this, is that you know, we've got these red points here. Okay, and then the green points, these are like the points that are considered little compared to the red ones. They're little in the sense that the green points are less or equal to all the red ones. So instead of saying find the smallest red point, what we're saying is, well, find all the little points, and then pick the biggest one of those. So the infimum of X is, in some sense, the biggest little point. And then we can turn that definition around and say, well, instead of the set of lower bounds, we can say the set of upper bounds. And instead of saying maximum, we can say minimum. So we have this other definition, supremum, which is the littlest big thing. Okay, but what I want you to see is that there's a sort of a weakness in the concept of minimum. Because, for example, right here, there is not a smallest red point. Yet, you want to be able to say 14. Okay, so now that we have that, so I could say similarly, sup of x supremum of set x is sup x is min of the set of all upper bounds of set x. Okay, so now we can finally state the fundamental theorem of analysis, and that is the following. So fundamental theorem of analysis. Okay, so now I'll say let AN be a sequence. Let AN be any old sequence there. So if two requirements. So first, AN is monotone decreasing. Monotone decreasing. Can you remind me what that means?
It's only ever going down.
Right. So it means means that if you consider, for example, element AK, and the next one, AK plus 1. So here's two consecutive terms there. Two consecutive terms. Then what must be true about this one? Right, so this one, the one that came before, has to be greater or equal to that one. So if AN is monotone decreasing, and now I can say on some tail, which is to say that there exists an M which is positive such that AK is greater than or equal to AK plus 1 for all K greater than or I'll say greater than M. So what that's saying is that it doesn't have to be monotone decreasing at first. It can be doing anything it wants at first. So at first it can be going up and down and however you like. But if it is eventually monotone decreasing, it eventually gets to a place where it's monotone decreasing. And furthermore, 2, AN is bounded below. Which is to say, there exists an L in the reals such that AN is greater than or equal to L for all N. Okay, so now we've got these two requirements here. So we've got a sequence that can be doing any old wild thing in a head portion of the sequence, but eventually you get to a tail and it starts being monotone decreasing, meaning that every time you move one element forward, you have to be less or equal. And furthermore, this sequence is bounded below, which means that there's at least one number that this sequence never gets less than this number. So you might say, well, it never gets less than 13. You know, it does some crazy stuff, but never gets less than 13. Then what can we say? Well, it's a lower bound. So then it must be the case that AN converges. Now, here's the deal. We can't say what it converges to. You can't say what it converges to, so you don't know what it converges to, but you do know that it must converge. Now the reason for this, we can't really prove it here in this class, but here's the idea, is that remember that a sequence is really a function. And what's the signature of that function? What kind of thing do you input?
Natural numbers.
Naturals. And what kind of thing do you output? Reals. So what we're saying is that all right, we've got some L here. So this is L. And so what we're saying is that there's an L such that the sequence never goes below this L. And the sequence can be doing any old crazy thing. It can be going up some of the time, down some of the time, up and down, whatever you want to do. But there's a tail that once you get beyond M, the sequence is allowed to have its indiscretions of youth here, but once it gets beyond M, what has to happen? It has to be monotone decreasing, which means that it can be constant, meaning that it doesn't go down at all because it says less or equal, but it can never go up. It has to go down or stay constant. So like that. So what that's saying is that okay, well, let's consider. The input axis is the naturals, right? So this is naturals, and the output axis is reals. And so now we could take all of these red dots. We could take all of these red dots and we could plot them on the output axis. So then plotting all those points on the output axis, you'd see something like this. So plotting all those points on the output axis there. And here's the deal. Because of the setup, you can tell me what number is a lower bound for the set of all these red points. What number is one of the lower bounds? L is. And because L is a lower bound, that means that all of these are lower bounds also. So all of these points are in the set of lower bounds. Now the set of lower bounds might go a little bit further up. Maybe L is not the greatest lower bound. But the set of lower bounds is not empty. And that means that if we consider the set of all red points, because it's bounded below, then it has to have a greatest lower bound. So it has to have an infimum. And that infimum is what the sequence converges to. So this idea that you can take the set of all outputs and find a lower bound and confirm that the outputs are eventually monotone decreasing, that guarantees that there has to be a greatest lower bound. There has to be an infimum, and so the sequence must converge. But notably, it doesn't say what it converges to. Good. So believe it or not, that's the fundamental theorem of analysis. And all the time in a math class, you're always trying to show those two things. You're trying to show that it's eventually monotone and it's bounded. Once you have that, then it's like, okay, we win. Okay, so now we're in the next section, section 11.2, and we're talking about something else. Now I have to warn you that that there's a significant chance of confusion. So we've been talking about sequences, and that's a word that may be kind of new to you, and it starts with S. And now we're talking about a new word, series, that are intimately related to sequences, but yet it is a different thing. So don't confuse these two words. Okay. So here we go. In the first place, we have this thing called sigma notation, just to make sure that you know what this is. And now we've already talked about it, but just for my own comfort here, I'm going to say, well, let's consider the summation 0 plus 1 plus 2 plus 3 plus ... plus 2, 4, 1, 4. So, you could, in principle, write out all of those instead of writing an elision, right? Instead of writing ... So I'm saying add up all the numbers from 0 to 2,414. Well, that could be, that could be really tiresome to write out. So rather than writing that, or if you like, rather than writing out if we broke an area into 47 pieces, you wouldn't want to write 47 individual terms for each one of those 47 rectangles, right? You want to have some nice way to write it. So here's how we write it. The sum from I is 0 to 2,414 of I. So that's the way to write that. So the reason to choose that Greek symbol there, sigma, is because it's phonetically the same sound as S for summation. And if instead of that, if I said, well, how about add up the squares? So 0 squared plus 1 squared plus 2 squared plus 3 squared plus ... plus 2,414 squared, then how would we do it? Right, so still sum from 0 to 2,414, except now we're doing I squared. Okay, so now I have a question. What if I do this? What if I say the sum from instead of I is equal to 0, what if I say n is 0? N is 0 to 2,414 of n there. So are those the same? They are the same. And what if I think you can imagine I could probably use any letter in our alphabet. Okay? But smiley face is not a letter, but I'm going to just pretend that it is for a moment and say I'm going to go from smiley face is 0 to 2,414, and then smiley face squared. So other than the fact that smiley face isn't a letter, is that true? It is true. So the fact that I can change this thing from letter I and that formula that uses I to letter N and a formula that uses N, and letter smiley face to a formula that uses smiley face, the fact that you can do that means that this letter is called an index. An index, yeah. So then this is analogous to being able to say something like this. How about this x squared dx, and then from 0 to 1. So that's an integral, right? So then the answer is some number. I'm not asking you to evaluate it, but are we in agreement that the answer is some number? So what about comparing it to, say, this integral? How about that integral? Are those the same? They're the same. They're the same, so in the same kind of way that, whatever that number is, it doesn't depend on x. And whatever this number is, it doesn't depend on theta. Those are the same number. So in that case, in this expression, x is called an index, and in this case, theta is called an index. And here, I is an index, and smiley face is an index. Okay, good. So we've got sigma notation, which is a compact way to write sums. And then we've got a symbol inside of it called an index. Okay? So here's an interesting place to start. I'll say, let's consider, let bn be equal to 1 over 2 to n, like that. 1 over 2 to n. So now, first request is please write. So what is the domain for Bn? Right, it's all the naturals, right? We can use all the naturals. So sometimes you can't use 0 if there's like a division by 0, right? But there's no problem with that here. So I want you to write Bn for n equals 0, 1, 2, 3. Just those terms, not all of them, right? Just those ones. Okay, so then what's B0? It'd be 1, yeah. And then B1, half, good. And then B2, 1 over 4. And then B3, 1/8. Okay. Whoops. All right. So now I've got a thought experiment for you. All right. So here is the number line, and here is number 0. So that's 0 there, and then here is 2. There's 2 right there. So suppose that I do the following. So I say that you're gonna have the following steps. I'm going to say that you're going to start. So these are your instructions. So start at 0. Start at 0, and then for the rest of time, I want you to do the following. I want you to step half the distance. To 2. All right. So if you start at 0, then how far is it to 2? It's 2, right? So then half of that would be 1. Okay. So then so that'd be the first step right there. Okay. Now how far are you? 1. And so how far are you supposed to step? Half. Okay. So you step half. Okay. And then now how far are we? Right, that distance is half. So how far are we supposed to step? Half of half, right, which is a fourth. And now that's a fourth there. And how far are we supposed to step? 1/8. So now what I want you to observe about this is that that first step that we took, how long was it?
1.
It was 1. And then that second step that we took was half. And then the next one was a fourth. And the last one, at least of what we talked about, was an 1/8. Of course, those are exactly the numbers that we wrote right there, right? So suppose that I said do this 1,000,000 times. You really wouldn't be able to draw it, right? It would get all cluttered. You wouldn't be able to draw it. But you can imagine if you were to do it 1,000,000 times, you'd get really close to 2, right? But you'd never exceed 2. You'd never exceed 2 because if you ever did exceed 2, then that must have meant that somewhere you didn't follow the instructions, right? Because you're only ever supposed to step half the distance. So if you ever exceeded, that would mean you didn't follow the instructions. Okay, so then so here's this is the setup for a joke. So then infinitely many mathematicians go to a math conference. Okay, and for those of you that know the difference, I'll say countably infinitely many. And if that doesn't mean anything to you, then don't worry about it. So countably infinitely many mathematicians go to a math conference, and then after all the stuff is over, they all go to the local tavern. And the first mathematician lines up and says to the bartender, "Bartender, I'd like 1 pitcher of beer." And the bartender says, okay. And then, writes down that order. And the next one says, I want half a pitcher of beer. And the next one says, I want a fourth of a pitcher of beer. The next one says, I want an eighth of a pitcher of beer. To which the bartender says, all right, folks, y'all did this last year. And then just pours 2 pitchers of beer. Right? You get it? So if the bartender keeps adding, half of the previous ones, how many pitchers of beer are there going to be? There's going to be 2 at the end of the process, right? So what I'm telling you is that the following. I'm saying that if you take B in, and that's 1 plus a half plus a fourth plus an eighth, and you add them all up. So add up all of the B in. 1 plus half plus a fourth plus an eighth plus ... Well, that's 2. Okay, so now, this thing that we did here, this taking a sequence and adding up all the terms, that's a series. Okay? So, two different things, okay? A sequence is a function from the naturals to the reals, and as it happens, it's called a sequence, and that starts with S. And then we've got this other thing, which is where you're summing up the terms in a sequence, and that result also starts with an S. It's called a series. Okay. So here we have a definition. A definition of series. So I could say, let AN be a sequence. Let AN be a sequence. Then this sum, the sum from K is, and I'm going to say be a sequence. Okay, so just back up just a little bit. Remember, we've written a lot of sequences down, and most of the time I always ask, what is the domain of this sequence? And it's pretty much always either the case that you say that, oh, the domain is the naturals. But if we're talking about the harmonic series, then the domain is the positive naturals, because you can't divide by 0. So I'm going to write a 0 right here, but you need to understand that that could be a 1, or it could be an 11. It's wherever you need to start. So k is 0 to infinity of ak, which is to say a0 plus a1 plus a2 plus a3 plus ... Then that is the series of the sequence AN. Okay, so that's called a series. So now, sequences can converge or not. And as a result, series can converge or not. So here's a particularly easy example. I could say 1, let AN be equal to 0, which is the constant sequence that no matter what natural you put in, 0 comes out. It's not a very interesting sequence. But then I could say, well, how about what's the summation from k is equal to 0 to infinity of AN? So you could tell me the answer now. It's 0. Right? So then, if you take 0 and you add up infinitely many zeros, what do you have? 0. Okay, so that's not profound. Whereas if we take something just barely different, and if I say Bn is equal to, say, I don't know, 2,414. So this is still a constant sequence. So like the first term is 2414, the second term is 2414, the millionth term is 2414. They're all 2414. So then I could ask about, well, what about this? The sum of all the Bn's. Then what about this? Does not converge. Because, you know, after all, okay, what we're saying is that you take a 2, 4, 1, 4, and then you add a 2, 4, 1, 4, and then you add a 2, 4, 1, 4, and then you add a 2, 4, 1, 4. How big is it going to get when you do that infinitely many times? Infinitely big, right? So it doesn't converge. All right. Interesting. So how about this one? How about Cn is -1 to n? And then this is so significant that it has a name. What's the name of this thing? An alternator, right? Remember, this is a sequence, and so this sequence is called an alternator because, well, the first value is going to be 1, and then the next one is -1, and then 1, and then -1, and then 1, and then -1, and then 1. Okay, so it's alternating. Now, how about this one? Well, let's think about it. So if we take the first number, that'd be 1, right? And then we add the second number to it. Now, the second number would be -1. You add those together, what do you get? 0. And then you add a 1, and what do you have? A 1. And then you add one more number, and then you have a 0. You add another one, you have a 1. You add another one, you have a 0. So is it ever going to any place in particular? No, right? It'd be just like asking, you know, what if I went over to the light switch and said, you know, here's what I'm going to do from now until infinity. Every time the clock clicks, I'm going to toggle the light switch, right? Off, on, off, on. And I just keep turning it off and on. Then after an infinite amount of time, will I have converged to some specific state? No, I'll just click, 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 click. So this doesn't converge either. All right. Now, so currently we've been a little bit sloppy. So we need to say what exactly do we mean by a series converging? All right. Series convergence. And this is where convergence. This is where you know, if you've been sort of like zoned out a little bit, I need your attention for about the next 5 minutes, because this is like the whole shebang right here. This is the whole thing. So I could say let AN be a sequence. So any old sequence there. And remember that a sequence is a function that has inputs are the naturals, and outputs are the reals. And so, you know, assuming that it starts at 0. So these are the inputs. And then for each one of those inputs, we have some output, you know, like this. So a sequence is this, you know, just these red dots here. Okay? And it goes on forever. Of course, I can't draw infinitely many red dots. So when we've been talking about sequences, very often I've said more or less something like, there is an M such that blah, blah, blah. And as the picture, where the picture is concerned, that's like cutting the sequence right here at this point. So there's infinitely many red points in the sequence. I just can't draw all of them. But if I cut it right here at any finite point, right there, then there will be finitely many red points over here, and then infinitely many over there, right? That's just like saying if I had a bag of infinitely many M&Ms and I took out, say, 1,000,000 of them, how many M&Ms would still be in there? Infinitely many. So when you take a sequence and you cut it, right there, this is called a head. And I want you to observe that there are always finitely many. Sequence values. And this is called a tail. And there's always infinitely many sequence values. Okay. No matter where I cut, even if I cut like, you know, miles and miles over there, like at you know, n is a billion, that would just mean that I'm talking about the first billion, but there's still infinitely more. Okay, so from this sequence we will define a new sequence. And we're going to call it SK. Define a new sequence, SK, which is going to be the sum of the K head of A, N. All right. So from this sequence, we're making a new sequence. Okay. So what I mean by that, S0 would mean that we've cut off the first term of the sequence AN, and we just took that one. So S0 is going to be A0. Okay. Now S1, what that is that we're saying that we cut at 1. So that means that we cut off the first two terms. We cut off 0 and 1. So we're going to take those two, that head, those finitely many, and then add them up. This would be A0 plus A1. So what is S2 then? Very good. And not to bash it too hard, but maybe I'll do one more. So what is S3? Very good. So what I want you to see is that we're cutting a tail and moving the cut along. And what we're doing is we're summing the head. We're saying that, okay, well, the first one is going to be A0, and then the next one is going to be the sum of the first, you know, those, and then the next one is that. So notice notice that there's a pattern. There's a pattern, and that is that, well, if we were doing this all in a row, if we were doing this like, you know, if we were actually trying to do it, then the fastest way to, if you had S2 already, what's the fastest way to find S3? Yeah, you take S2, which you already have, okay, and then you add A3, right? So what I want you to see is that as a formula, I can write this over here and say that you know, this is just A0 there, and then what this one would be, this would be S0 plus A1. So that's not too much help, right? But the next one you get a little bit of help, because this would be S1 plus A2, and then this one would be S2 plus A3. So what I'm saying is that to get the next S, to get the next one, you take the previous one and add that element. Okay, so generally speaking, the formula will be this: that if we want SK, if we want SK, then on the one hand you could say that, well, that's A0 plus A1 plus A2 plus ... And what's the last one that we add? AK. But, you know, K could be like a million, you know? So that'd be a lot of writing. So one shorter way to write it would be what? So if we want sk, what's the name for the previous one? sk minus 1. And then we add to it what? ak. Okay, so this is the new sequence. So we started with the sequence A, and from that sequence we're making a new sequence, S, which is obtained by taking moving a cut down the line and saying, as the cut moves down the line, we're going to just be summing up the head and leaving the tail for later. This sequence is called, so this is called the sequence of partial sums. Of AN. Because it's saying, well, let's imagine what it would be like to find the series of AN. Well, you'd have to start with the first term, and then add the next one, and then the next one, and then the next one. Well, that process amounts to this sequence. So I'm just saying what you would do. So you say, so the statement. Or the statements. So first, the sum from k is 0 to infinity of AN converges. So that's a statement, because the sum may converge or it might not, right? We've seen two that are going to converge, and we also saw one that doesn't. So the statements, this converges, so that means SK converges. So now we're using converges twice, okay, in that sentence. So you need to understand that this one in red, to say that this converges. So this is a series. We're talking about whether or not a series converges. Whereas this one over here in green, what kind of thing is SK? It's a sequence. So over here, this box over here, the word converges is talking about a sequence. So to say that a series converges is to say that the sequence of partial sums converges. Similarly, if not only do you know that it converges, but moreover, you know that it converges to L. So, for example, in the silly story where we said, all the mathematicians after the thing, all the countably many mathematicians go to the tavern, okay, and then they order, one pitcher and then half a pitcher and then a fourth a pitcher and blah blah blah. After you do all that, after you suppose that the bartender keeps pouring it into pitchers, how much will you have? 2, right? So to say that a series converges to a specific number, like 2, that means what? Right. It means that the limit as k goes to infinity of sk is L. So this is saying a statement. The series value is that. That means that you construct this sequence, compute the limit, and it's that value. That's what that means. All right. Good times. So any question about this? Okay. Good. So now, we have like 30 seconds to do something new. All right. So here we're going to have one. I could say, well, what if those mathematicians who are playing the joke on the tavern manager or whatever you call that person, the bartender, what if instead of saying, I'll have one pitcher and then the next one says I'll have half, instead of that, what if we have the following? What if we say let AN be equal to 1 over 3 to n, right? So it's exactly the same problem, except instead of 1 over 2 to n, it's 1 over 3 to n. Suppose that, we could write down a0, well, that's 1. a1, that's a third. A2, that's a ninth. A3, that's a 27th, right? So you walk up to the bartender and say, oh, I'll have one pitcher, and the next person says, I'll have a third of a pitcher, and the next one says, I'll have a ninth of a pitcher, and the next one says, I'll have 1/27th of a pitcher. So we couldn't possibly exceed 2 pitchers, right? We couldn't exceed 2 because we already established that if we do it with halves, if we do it with halvesies, then it couldn't be more than 2. So if we're doing it with thirdsies, thirds, we still couldn't get less than 2. So here's the thing: the sequence of partial sums. Do you observe that if we say 1, and then 1 plus a third, and then 1 plus a third plus a ninth, and then 1 plus a third plus a ninth plus a 27th, do you observe that the sequence of partial sums is monotone? Do you observe that there's always going to be a little more? Yeah. At every step, the bartender puts a little splash in there. So we're talking about a sequence of partial sums that's monotone. Is it bounded above? Is there some biggest value? What's an example of an upper bound? 2. Right? It couldn't exceed 2. So we're going to make a sequence of partial sums that is both monotone increasing and bounded above. Is it going to converge? Yes. Why is it going to converge? I'm fishing for a phrase that starts with F and ends with fundamental theorem of analysis. Oh, you got it. So we're going to make a sequence of partial sums that is monotone increasing and bounded above. Must it converge? It must. And we're going to do that next time. So have a nice Monday.